Welcome back to another OpenGL GLSL tutorial, and this time we are going to take a look at three topics. One is cube mapping. Cube mapping is a relatively simple topic. It's another kind of texture. Next to the texture 2D, which we have used so far. It's not too complicated. It will be relatively easy. Then we are going to recreate this skybox. We already had one skybox with this cube mapping technique. It's an interesting technique to use for skybox, but it's pretty cool, I think. Alright, the last thing which we are going to take a look at, more precisely the last two things which we are going to take a look, one is the reflection. As you can see, this monkey head is reflecting its background. Pretty cool, huh? And another technique is the refraction. This monkey is transparent and apparently using refraction to make the modification or transformation when the light passes through this monkey head. And of course, we are also going to use modern OpenGL. We are not going to introduce any depraved functionality. We are going to use static cube maps, which means that you can't actually see the reflection of the other monkey in this monkey. And if I go here, you can see the other monkey through this monkey. You can see it's there, but it's not there when I'm looking through this monkey. You can solve this issue by dynamic cube mapping. Dynamic cube mapping pretty much means that you go here to the center of the monkey, right about here, and you take 6 images. So you take an image there, 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 and make a cube map from that. Of course, you can do it by now with the frame buffer object. So you just render the cube, render with the help of the frame buffer object to the cube map, and then you have fully dynamic reflection and refractions. So if the player is, I don't know, standing in front of the monkey here, it will see itself, so the player. Right, that was it about the demonstration. By the way, if I just load up for the demonstration another kind of program, which is not as complicated as the monkey, but just a simple sphere. So let me just load up a simple sphere, OBJ, and right, I am compiling. Then you can easily see that this is indeed a reflection. As you can see, there is this big blooming effect, as you can see, and you can see it on here, on this sphere. And also you can see that indeed it's working like a magnifying glass, so it's magnifying kind of effect. It's great. Of course, you can change these effects relatively simply, for example, how much the magnification, more precisely, how much the reflection index is. Refraction index, I wanted to say. Alright, so actually let's go into the program. I loaded up a program. This is pretty much the simple matrix program which we have created. And let's see what did I modify on this program. Not too much. Basically, I'm not rendering on the frame buffer. We don't need post-processing and stuff like that for now. I'm just simply rendering out this monkey geometry right here with the scene.draw. And let me actually compile this program. It's not this terminal, it's this terminal. So if I just go here and compile the program, you can see, oops, an earlier try. Okay, so you can see that this program is nothing special. It's just a pair fragment lighting, and you can move with the camera. So we are going to transform that into the program which you have seen previously. So by starting that, let's make a cube. So to make a cube, making a cube is a relatively simple process. We just contain 8 vertices, and because we are using triangles, it contains 12 faces, if I'm counting correctly. So let's make another mesh. We had a mesh called quad right here, so let's make another mesh called cube. So we are now just making a cube. This is not reflection or refraction topic. It's not even the topic of cube mapping. I'm just creating a cube. I can create a cube, right? Or I could load one from file, but because cubes are relatively simple, I'm just going to create one. So to create one, I actually started GIMP, so we can actually visualize how we are creating it. So right here, I'm just going to draw a cube. So right here, and back there, back there, back there. Okay, it's not really too cubish, but approximately okay. So I'm going to define the vertices in this order. 1, 2, 3, and then here 4, 5, which is not seen on this image. Let me just make it like that, so we can see it. It was 6 and 7. 6, wanted to be 6. So what I'm going to do is just go from the center, go 1 unit to the right, 1 unit forward, and 1 unit up. This is what I do basically. But before I do that, let me just copy this 3 line right here. So the temporary indices, vertices, and TMP. structure right here. So I'm just going to modify the position, modify change, and then go 1 to the left. This is what I said. Go 1 to the up, and go forward 1.0. Simple enough. I'm also going to add a color to it. So for demonstration, or not demonstration purposes, but for testing purposes, I'm just going to add the color. So color, the change, and I don't know, let it maybe be red. Perfect. And I'm just going to push it back to the vertices. So vertices dot push back, and I'm just pushing back the TMP. That's simple enough. I'm just going to create copy this. So copy this and here, and copy this, and one more time. So now it starts with the 1, so continues with the 1. So left, down, forward. So the only thing I need to change is put a minus sign right here. Then we are going on a positive, and we are still on and still down. So positive and still down and forward. Right, and the last one will be, we are going positive, we are going up, and we are going forward. So 1 positive, 1 all of them for these 3 vertices, 3 vertex number 3. So what I'm going to do is just copy these and paste it right here, because the back vertices are exactly the same as the front vertices, except they all go back. So I'm just going to push a negative sign to the Z everywhere. Incredible, we have a cube defined, but these are just the vertices. We haven't defined the faces. So what we have to do is actually use these as indices. So 0, 1, 2 is forming a triangle right here. A triangle, and then 0, 3, 2 forming a triangle, and then we have the front face. Now we have to do just this for all of the vertices, all of the faces, which is 12 faces. So I'm just going to use indices dot push back, and I'm just going to write 0 here, check if no mistake here, because I'm going to copy paste it. So 0, 1, 2 define a face. Then let me copy that, and then what else defining a face? 0, 3, 2. So I'm just going to write 0, 3, 2. Perfect. Then we are actually finished with the front face. We don't need to care about the front face anymore. Let's start with let's continue with the left face. So 2, 3, 6. 2, 3, 6. Pretty simple stuff. I'm basically just copying, so it's a quite boring part of the tutorial actually. The interest come later. So 3, 7, 6. 3, 7, 6. Cool, we have the left face. Should I add comment left face? And this is the front face. Okay, and we need, now let's go to the back face, and let's see what vertices make up the back face. 4, 5, 6. 4, 5, 6. So right here I just write 4, 5, 6. Okay, and what else? 4, 7, 6. 4, 7, 6. So 4, 7, 6. You might want to care about the winding order to make sure that all of the vertices are defined in clockwise order, not anti-clockwise, because you may want to call the outer faces, because you are inside the cube for now actually, because we are going to make it as a skybox. So we have finished with this face and this face. So let's go to the right face. Right face is 0, 1, 5. 0, 1, 5. This is the right face. Right face 0, 1, 5. What is the other face? 0, 1, 5. What's this? So 0, 5, 4. So 0, 4, 5 rather. 0, 4, 5. Cool. Let's see what else we have. We have the top face. Okay, so the top face. Let's see the top face. 0, 3, 4. 0, 3, 4. 0, 3, 4. Again, you might want to put it into a header file so it will not take up the place right here in the main file. But I'm just going to leave it right here. So what is the other? 3, 4, 7. 3, 4, 7. Cool. One more face to go and we are finished. The one more face is the bottom face, which is 1, 2, 6. Let me write it here. Bottom face. But I forget it now. 1, 2, 6. Right. 1, 2, 6. 1, 2, 6. And the next one is the final one, which is 1, 5, 6. 1, 5, 6. Perfect. I think we are finished, but we should draw it out to see if we really did. So I'm just going to call the cube draw, although we don't have really lighting going on because we haven't defined a normal vector for this. So for the cube, so the lighting calculation from the main shader will basically not work, but we will see something if we define it correctly. This should be our program. Oh, one thing I forget, we should actually make it so cube equal to a new mesh, and this new mesh contain vertices and indices. Okay, did I create the cube? Right here, I did. Did I delete the cube? Nope. So let me just delete the cube. Okay, delete the cube. And let's see what's going to happen if we run this program now. We should see a completely black cube, I believe so. So let me just compile it and run it. And we have indeed a black cube. Okay, we have the cube, so now we are ready to draw this cube actually as a skybox. If you have watched my earlier tutorial on skybox, you know that the skybox should be drawn between the control and the update camera function. In this way, the rotation applies to the skybox, but the translation not. So pretty much we are not getting closer to the skybox because we assume that it is infinitely far. So what I'm going to do is actually copy this part right here, actually cut it and put it there between the control and the update camera function. So now if I compile the program and run it, we should see a big black screen. Do we see? Kinda. This happens because our close, so the near cutting plane is one distance, exactly the same distance as our cube's far plane. So we are just changing it to 0.5, and then we should see a big black face everywhere we are looking at, because we are on the center of the cube. As you can see, we can't see anything. Right, this is exactly what we want, a big black screen. Although one thing I noticed whenever I tested this code, that I screwed up something right here in the camera.cpp. Whenever we have this camera.control and the camera.update camera, it's not automatically modifying the view matrix, it's modifying the currently attached matrix, whatever it is. Although right here I attached the view matrix, and as you can see, it's good for the control. But for example, right here somewhere, we modify it back to the model matrix, which is cool. We have to modify it back. But then this update camera is not okay right now because it's modifying the model matrix, which is not cool. So if I will just write it down here, everything will be fine. But I would rather make the change in the camera.cpp file. So I'm just going into the camera.cpp file, and right here, whenever we are rotating, I'm just going to change the matrix mode to view matrix, and then change the matrix mode back to model matrix right here, and change it back to model matrix. In this way, we are always modifying the view matrix whenever we call any of the camera's function. And this is exactly what we need. We want to modify the view matrix. It is important, especially for now, because we are handling the view matrix and the model matrix separately for this tutorial, because reflection need the model matrix separately. This is a very important thing. So make sure that the view matrix is not somehow combined with the model matrix, because we need it separately. Okay, I can't stress that enough. Right, so let me just draw out the monkey, because we want to see the monkey as well, so we know that everything is working. So I'm not going to clear the screen now because we want that black cube. So I'm just delete the clearing function, and I'm just call the scene draw, the scene containing the monkey. So if I compile it right now and run it, we should see a black background and the monkey. Alright, and here is another problem. We should disable the depth testing for the cube, because as you can see, as I get further, the monkey gets outside of the cube. So why it is happening? Because our depth testing is enabled right here. Depth testing is enabled. We draw the cube with one distance, and then when we are moving back, basically the monkey is getting outside of the cube. So what I'm doing right now is just disable the depth testing while we are drawing the cube map, and enable the depth testing when we are enable the depth testing when we are drawing the monkey head. So if I just compile it right now and run this, then we should have a monkey and exactly what we need. Alright, so let me make a shader which actually drawing the skybox. For now, let's just draw the colors so we see that it's indeed working. So I'm just going to call this skybox shader.frag, which going to draw the fragment, which going to be a fragment shader, and it's going to draw the skybox. We don't actually need the vertex shader, because the vertex shader for the quad rendering should work here. So what I'm going to do is make the main right here, do we need anything, the out color? So varying vec3 out color. If you remember vertex shader, let me open up the vertex shader. Wait, I think we have modified that property. Does it send out color? No, it sends only the UV coordinate. Then let's make a vertex shader as well. So I'm going to call this skybox shader.vs for the vertex shader, and let me open this up, and it will be very simple. Just I need to, that's not the, I'm going to need to open up the original vertex shader right here, and I'm going to copy a few stuff like these few stuff into our vertex shader. So basically just the attribute values, the input, we always need those, although we are only needing the color and the vertex right now. Then we have a few varying variable. What do we need? We don't need the normal, we don't need the tangent, we need the color, we don't need the UV coordinate, neither the position. And then have a lot of matrices, and they are never good if they are there. Alrighty then, so we have the position, that's cool, and then send out the color. So the out color equal to the color, and it will nicely interpolate between the two color. You remember how it's working from the first tutorial pretty much. Now let's just draw the fragment with this color, so gl underscore frag color, and let's make it a vector 4 with the out color and 1.0 alpha. So now if I just load it up, so I'm go upward and create a new shader, another shader. We will have a lot of shader at the end of this tutorial series, by the way. I'm just going to call this skybox shader right here as well. Then let's initialize this shader just as we did with the other shaders, so equal new shader with the skybox shader.vs and the skybox shader.frag shader files, and let me just delete this shader. So delete shader, and what we have to do is actually skybox shader, and what we actually have to do is use this skybox shader to actually draw the skybox. So I'm not going to use the main shader, I'm going to use the skybox shader. We don't need the camera position for the skybox, neither the light position, so I'm just going to delete those. And actually we don't need even clearing, because as we draw the skybox it will automatically clear because it will overwrite everything which is there. Maybe we only need to clear the depth buffer, so let me go back. We are clearing the depth buffer somewhere right here after we enable the depth testing, because you know we need to clear the depth buffer, but we don't need to clear the actual color buffer because we're drawing a big cube right there, and it will automatically do the clearing for us. So let me see if it is working. So I'm just compiling and running, and we have white everywhere. Why is everything white? Of course, we have a mistype varying. Although I just realized we didn't even change the color anywhere, so let me just quickly change the color because it will be red everywhere. So just randomly popping into colors right here. This will be white, and this will be whatever color this defines. Right, but we have a mistype varying, the R coming here. Let me see now. Alright, we need to clear the screen, it seems like. So apparently our skybox won't draw, and I'm not quite sure why it's not drawing, but let's see. We define the GL position. It should draw. Oh, you know what? I forgot to change this to skybox and this to skybox. And now it should draw, and we don't need clearing because skybox will clear the screen. And there we go. We have a big box around us with different colors on the different vertices. Not too interesting, but now we are ready for doing the cube mapping because we already have a cube. So I'm just going to make a function somewhere which is going to load in a cube map. Cube map is a 6 texture, so it will return the ID of the cube map, similarly like a GL texture 2D. Unsigned in and load cube map, and it will actually wait an array of strings. So std string, and just calling file names because we have 6 file names in this. So 6 file names. Right, the load cube map will be relatively simple because it's almost like loading a texture 2D, except we are doing it 6 times. So I'm just going to make an ID right here, so text, and then I generate textures, so glgen textures one texture to the text. So far it's exactly the same as a normal texture 2D. Then I'm going to bind it, so GL bind texture, and here is the trick. I'm not using GL texture 2D as I used to, but I'm just going to use GL texture cube map. Okay, so and of course, what texture do I binding? So this is how we are binding a cube map, pretty similar to 2D texture, except it is cube map. Alright, and I'm going to write a for loop which is going to loop 6 times, because we have 6 textures in a cube map. Cube map, I haven't actually defined what a cube map is, but pretty much it is a cube, and every face have a texture, a simple 2D texture on it. And then in the GLSL we are going to use a 3-dimensional vector, for example a direction vector. Oops, that wasn't too straight. Okay, so here is a vector, and then this vector is just defining a point on the cube map, and yeah, this is it, but it's later. We are just now loading the cube map. So what we have to do is go through 6 times. Then I'm going to load the texture, so I'm going to make an SDL surface, and I'm just going to call it IMG, and I'm going to use the load texture function. We are going to create this function, but basically just loading an image to SDL surface, and the file name's I. So I'm just going to load the eyes texture. By the way, the order is important how we pass the texture. Let me actually write it right here. First we need the left, then we need the right, then we need the top, then we need the bottom, then we need the near, and then we need the far. So this is the order how you should pass basically the file names. Okay, so I have loaded an image. Now it's time to actually create GL text image 2D. I'm using the same function as I have used to, except now the first parameter is the only one which is different, which is GL texture cube map positive x plus I. Very tricky, but what it does, let me open up the GLE header file, GLE, to see how the constants are. So GL texture cube map. So GL texture cube map positive x. So this is why we need to put the right texture at the first. Then negative x, which is why we have to put the left at the first. And as you can see, there is only one difference between the constants. So what we can do is actually just adding I to it. So adding 0 to it, meaning that, oops, I accidentally swapped this too. This is right, left. So what it is, I didn't swap the other one though. So what we have to do is add I to it. So first of all, we add 0 to it, which is going to put this texture to the positive x, so the right side of the cube map. Then we add 1, which is going to put it to the left side of the cube map. Then we add 1 more, that this will going to put it to the top of the cube map, then the bottom of the cube map, then the near plane of the cube map, and then the far plane of the cube map, basically. So this is how it's working. It's a pretty common technique to use to add I to this constant. The other parameters are exactly the same as we would just creating a 2D texture. So the next one is the 0, this is the border, then the type GL RGB 8, or actually use GL RGB because that's what I used in the original image loading tutorial. And then the next parameter is the width, so IMG width, then IMG height, then again write 0 because this is the, oh no, this was the mapping level and this is the border. This function has so many parameters, I always forget the order. So GL RGBA, then we are using GL unsigned int underscore 8 underscore 8 underscore 8 underscore 8, and then I'm just going to use IMG pixels. That's it. So this is how I loaded the image in the original tutorial about the image loading. Let's just set the parameter similarly than we did pretty much every imaging texturing tutorial in OpenGL. So GL text parameter I, and then the only difference is that the first parameter is the cube map, GL texture cube map, and the second is the same as we usually set, so GL texture mag filter, and just set it to GL linear. Okay, let me just copy it right here. This is the min filter, is GL linear too. Let me just copy it again, and then we need the wrap S, which is GL clamp to edge, so it's pretty much repeating the edge at the edge of the texture. So if we give greater number than 1 or less number or smaller number than 0, wrap ST. Okay, we have defined the 4 parameter which we need, although we actually technically need the first 2. The second are just so it will not be repeating texture, because then we have the black line at the cube edges. And now we are just going to free this image, so SDL free surface and img. Alright, then we need to make this load texture function. I'm going to cheat a little bit and go up to right here to my scene loader, I think, and it should contain one of these. Copy exactly it's containing right here. So I'm just going to copy this and paste it to the top of the file right here. Now, though we will make some modification on this. For example, it's not in the mesh loader. It's going to get actually a string reference, so std string reference file name, and we are going to use the cstr member function of the string, because this is a std string and we need a c style string right here. Let's do the write out, we do the conversation, and let's free the surface as the free surface. Let's free the original image, we no longer need it, and return with the img2. Okay, and I'm just going to delete the rest of the stuff. And here just write null instead of -1. That should do the trick. This is going to load an image from the file and then convert it to the format which we can pass into OpenGL and return with the pointer. So, almost forget it, SDL surface pointer, and return with the pointer to that right here. And then we are just going to load all the 6 textures and also freeing them. Oops, again. What button do I press in continuously? And then just return with the texture from the cube map. That's right, I believe we are finished. Although also I like to just bind 0 to here so we don't accidentally use the texture cube map. So we are not binding any texture basically with the 0. And let's load this cube map somewhere. So I'm just going to use this load cube map, and the init should be a sufficient place to load a cube map right here after we define this cube. And I'm just going to make a cube map variable in a moment, and this is equal to the load cube map, and we need an array of strings. So std string and file names. Okay, this file name is containing 6 strings, so let's make the first one. So I'm just going to copy a not from here, but I made once upon a time I can find it over. Once upon a time, I have made skyboxes right here, as you can see. So I'm just going to copy actually the entire folder, just going to copy it to our folder. By the way, if you don't have these skyboxes, just go online, search for skybox, and then if they are on one image, which pretty probable, then just cut out the 6 different faces and then just call it back, bottom, front, left, right, top. So according to the names which their face are on. Okay, so right here, the first one will be skybox slash, then the order is right first, right.bmp. Oops, we don't need parentheses. Then the next is the left.bmp, left.bmp. Then the next is the bottom.bmp. The next one is the top.bmp. The next was which was it? The near was it, I believe, so the far was first. The near was first. So let me just put it near.bmp. Actually, I didn't call it near.bmp though. I just remember what did I call it? Not near, but I called it front and back. So front.bmp. And the last one is back.bmp. Back.bmp. This is 0, 1, 2, 3, 4, 5. And we have it. Okay, so I'm just going to give this file name apparently. So file name to the load cube map function and create the ID for this cube map right here somewhere. So unsigned int cube map, and let's see if we actually made any error. We did, because this is not position x, this is positive x. So let me just go into here. This is positive x. I'm not sure why I wrote position, but I did. So let's compile it, and if it's compiled, then we are ready to move on. Alright, we have the cube map, although we haven't used this cube map for anything. So let's actually use the cube map and demonstrate how to use a cube map in the shader. So let's go to the skybox shader.fragment, and this is a uniform sampler cube. This is a sampler cube, not a 2D texture, but a cube map. So this is how you tell that you are going to use a cube map. And I just call this cube map. Now, to get a pixel of the cube map, you have to use a function called texture cube. The texture cube waits first the cube map, which is cube map. The second parameter is a 3-dimensional vector, so something in here. Now, what interesting thing could we do with this? For example, what we could do is just getting the position of the vertex and then use it as a 3-dimensional vector. So let me go to the vertex shader and let me make another varying variable, varying, and this will be a vector 3 as well, and I'm just calling it vertex position, or make it, let's call it vertex vector. The vertex vector is a vector which is pointing to the vertex. So how can we get a vector which pointing to the vertex? It's fairly simple, it's just the vertex itself. So vertex, with an E right here, vertex vector equal to the vertex. Nothing special, just make it equal. So we actually pass it to the fragment shader. And right here, let's just weight it. So let's put this right here. And let's use this as our position, so vertex vector. And this should actually give us the whole cube map without actually anything else to do. The only thing which we will need to do is actually pass this cube map to our shader. So I'm just going down to the display right here, and I'm going to bind this to the texture layer 0, so GL active texture GL texture 0. So I'm going to use the 0th texture layer and GL bind texture, and I'm going to bind GL texture cube map, not 2D, and I call this cube map. And I'm going to pass it to the shader. It would be cool if I could copy somewhere. Okay, one important thing which we should never forget is to change the program name. And this is a 1i because I'm going to pass in a cube map or a texture, and this is just 0. Oh, I see no problem right here, so let me just try to compile it and see what this is going to result. I hope it will work. Or not. Why it's not working? Oh, I know why it's not working. We just get the color, but we don't actually make it equal to the fragment color, so the color of the current pixel. But now I think it should work. At least I hope so. So let me run this, and we swapped up the top and the bottom, so we can easily fix that by go here where we defined it and change the top and the bottom. So this will be 2 and this will be the 3. Let me just check the Y. Positive Y, so we should start with the top and not the bottom. Alright, I can live with that. But now if I run this, we get a perfectly functional cube map, or skybox if you would like to call this in that name. And it's only using cube maps. Of course, you could just go into with the trivial solution, so use 6 normal quads, which we have already created quads, rotate it and translate it to the to the correct positions, and you get the whole skybox thing going on. Alright, let me go back to a little bit to the skybox, maybe it wasn't clear. So if you have a cube map, so right here I just draw a cube map similar to what I have before. So right here you just have a cube map. For now I just draw it like a simple cube. Then in order to get a pixel information, you start off from the center basically. So right here somewhere the center, and you just make up a 3-dimensional vector, or tell a 3-dimensional vector to the texture cube function. For example, I'm telling this vector right here. It don't have to be actually normalized vector, but any vector will work. So you just tell a vector, and from that vector, it's pretty much we're going to find out which pixel it is. So what I did in the program, I get the vector, which is, for example, right here, the vertex position, and of course this is interpolated nicely across here and nicely across the entire plane, so everywhere it's nicely interpolated. And then of course it is interpolated, and then another vector, I just get it here, and I get the position what the skybox value, pixel value is there. I'm not sure if it is completely clear. It's not too complicated. One thing you have to be very careful about, that this is all defined in word position. So this vector is defined in word position. Let me show you an image which I found online on the interwebs. This is how basically the matrices work. You have the object space. This is the space where you just define your object basically and the normal vector. So for example, in a case of our cube, this was -1, 1, -1 and stuff like that right here. Then we multiply this by the model matrix and we get to word space. This is not the final position yet because of course the camera can move and the view matrix is containing the camera movement. So right here, after we multiply by the model matrix and the view matrix, or if you like the model view matrix, we get into camera space, and then after projection we get into the screen. But we need to have the vectors in this space, the word space right here. In order to get to the word space from the object space, we have to multiply by the model matrix. It is important, and this is why we don't like to have model view matrix, which the default OpenGL provides. So finally we have some usefulness of the matrix which we actually have defined instead of the building matrices, because now we have a model matrix. We don't have to get the model matrix from the model view matrix, although this is possible, by multiplying with the inverse of the view matrix. So let me show you an example in just the numbers. So if you have a multiplication like 12 is equal to 3 times 4, right? Now, you know the result, and if you know one of the component, then you can calculate the other component by multiplying the inverse of that. For example, the inverse of 4 is 1/4, or 0.25, and you just multiply it here and you get back 3. It works similarly for matrices. You know that there is a GL model matrix, these are the building matrices, so GL model matrix, and there is a GL view matrix, or GL_view matrix. Oh, caps lock. Anyway, so and then that make up the GL model view matrix. And you know the model matrix, model view matrix, because this is provided for you. And then if you just get the view matrix, this can be a little tricky, but you can get it. Then if you multiply the inverse of the model, so the inverse of this inverse of the view matrix, then you get back the model matrix. This is how it works. It works the same way as in case of numbers, but calculating the inverse in everything could be a little bit expensive. So we have now the separate model matrix, so it's pretty cool. We don't have to calculate with inverses. Let's see, what else should I tell? Of course, you don't want to apply translation, so the last column of the value, you remember the last column of the 4x4 value is the translation to the normal vector. You only want to apply translation to the actual vertices. And yeah, that's pretty much should be enough for now. So let me just create another file. We are going to, not in this file, not in this folder, but this folder, we are going to create another shader. Actually, we are going to create a refract shader, and we are also going to create a refraction.vs, so vertex shader. These two is a relatively simple shader. Let me start with the vertex shader. And let me start by copying a few things from the vertex.vs file, because we don't want to type all of this stuff again and again every time. So I'm just going to copy it here. We actually don't need that many varying variables. What do we actually need? Let me think. We might need the normal, because later on we might want to add lighting next to the reflection. We don't need color, UV. Okay, we can keep the UV coordinate as well if there is textures on this monkey head, but for now there will be no use of the out UV. Alright, and we will actually need some other varying variables as well, but let's go here, and what do we need is actually we need the vertex position. As you may remember from the little figure I just showed you earlier, we have to multiply by the model matrix, because we are in the object space whenever we, or model space if you would like, whenever we defined this monkey head. So we have to multiply by the model matrix. Let me actually do that. Model matrix times the vertex. But don't forget that this is a 4x4 matrix, and the 4x4 matrix can be only multiplied by a 1x4, so basically a 4-dimensional vector. So just press 1.0 at the last parameter, and let's cast it back to vector free. We don't actually care about the last parameter. Okay, so this is one varying variable, so varying vec free word vertex position. And let me make another vec free variable. This will be the word normal position, or actually this is rather direction, because normal vectors have direction. So the word normal direction is the same. We have to multiply by the model matrix except the translation. We don't translate. So what we are going to do is cast the model matrix to a mat free. By the way, it is only work if we have this line here, which says that version 1.2, so 120, because this is the lowest version. The matrix casting basically is allowed. So this is going to cast down or cut down the last row and the last column of the matrix. And then I just multiply this by the normal, and then I get a three-dimensional vector, which is the word normal position. Let me see, do we need other thing? Alright, let me go back to a little bit to the skybox. I don't think we will need anything else for the reflection, so for the vertex shader. So let me go to the fragment shader. Let's copy these varying variables because we might need them, and also make sure that this file is version 1.2 as well. We also need the cube map, so let me create an uniform sampler cube map, and let's go to the main. This will be a relatively simple process because we have a built-in variable called reflect, which calculates the reflection vector, though the actual equation is not that complex either. So we need an incident vector. Let me actually draw a little bit. I feel like I want to draw something. Let me just delete whatever was drawn here previously. So we have a surface. So like this, for example, this is the head of the monkey. Then we need an incident vector right here. This is the vector which basically goes in. This is called incident vector. We need the normal vector of the surface. This is the normal vector of the surface. And then we get the other vector, which is the reflected vector. We actually use the reflect function for the specular, right? I believe so. And then we are going to use this vector right here, which we get as the sampler cube vector 3D, and then we get the reflection right here from the cube map. This is basically it. There is nothing too complicated in this. So let's make a vector 3 incident. This is the incident vector, and this is actually the normalized version because we should have normalized incident vector. We should have normalized incident vector. I'm not quite sure about that. Maybe just the normal need to be normalized. The normal definitely need to be normalized, but I'm not sure about the incident vector. We will try in a moment. In the original program, use normalized vector, so I'm just going to use it right now. We need to get the position. How can we get the position? You remember basic vector algebra. If we have a position right here and right here, we want to get a vector from this. Then we just use the endpoint minus start point. What is the endpoint? The endpoint is the word vertex position, because we want to calculate a vector right here, which pointing right here to the position. And what is the other position? The other position is actually the camera position. So let me actually get it as a uniform variable as well. Uniform vec free and camera position. The camera is already have the position in workspace, so we don't have to worry about that. Just subtract the camera position from this. And now we have the incident vector. The other thing is the normal vector. So let me create a vec free normal, and this normal vector, then this normal vector will be just simply the normalized version of this word normal direction. We have to renormalize it just to make sure that it is normal length, so it has the length of 1. And then I'm just going to get the reflected vector, vec free reflected. The reflected vector can be get very similarly by just using the reflect function. The reflect function first parameter is the incident vector, and the second parameter is the normal. That's it. We get the vector, and now the final thing is coming. So GL frag color, and let's just make the frag color equal to the texture cube. So I'm just going to use the texture cube to actually do the texture lookup, which is first of all the cube map as the first parameter, and the second is the vector, the reflected vector, because we are going to make the color of this pixel equal to the reflected stuff. I think it's quite clear. So I'm just going to write reflected right there, and there we go. I think this should work. But let's try it out, because what I think is not always how it works. So make a shader, and I'm just going to call it reflect shader. Reflect shader. What a nice name. Okay, and let's delete the reflect shader at the end. Delete the reflect shader, and let's initialize it in the init. So reflect shader will be initialized right here with a new shader, which is the shaders which we have created, which is the reflection shader. Did I call it reflection shader? What did I call it? Reflection.frag and reflection.vs and reflection.frag. Good. That's right, we have the reflection shader, so let me use this reflection shader to draw the monkey head. So I'm just going to change this main shader to reflect shader, reflect shader, reflect shader, reflect shader, and here and here. Ooh, that's a lot of reflection shader. We don't actually need the light position right now, so let's comment that out, but we need the camera position because we actually get the camera position. We also need the cube map. I'm just going to copy it, this part right here. We are going to bind the cube map to the texture layer 0, and then bind the cube map, and then just giving the position cube map. Okay, why does it have light pose? It's cube map. We might have luck that it's exactly the same ID. Anyway, so we bind the cube map, and which is capital M, cube map, to the texture layer 0 with the shader, so with the reflect shader. And do we need anything else? We have these two uniform which are filled up, and no, we don't need anything else. So let me just try to compile this program and run this. So as you can see, it's compiling right now, and still compiling, and running this, and let's see, we don't get actually error. Nothing seems to work correctly. Why it's not working correctly? Let me just do a quick debugging section. Alright, I'm just finished with the quick debugging section. So the only thing which we actually need to do is copy these GL uniforms after we actually use the shader. Alright, so here this is as well. So just make the GL uniform after the use shader, which should be quite obvious that they should be there. But I don't know, they kind of work sometimes without before the actual use shader. I'm not sure. From now on, I'm going to put it there, and as you can see, we get back the same program as we had earlier. We had nice reflection from every part of this monkey head, and yeah, here we have. Let's quickly modify this program to make it a refraction. I'm not even going to rename anything because they are so similar. So the only thing which we actually need to do is not using the reflect function, but using the refract function. The refract function will have one more parameter than the reflect function, which is the refraction index. So this is a number approximately 1, near to 1, like 1.2, for example. This is the eta. And actually, if you go online, so let me just go here and go online to somewhere like Google and search for refraction index list. Then you have a list of refractive indices, and here are they. So just divide the thing you want to actually do the refraction with. So right here, I don't know, search for glass. Here is the glass, it's 1.4. Then here is the air, which is actually 1, and you know, just divide it, and you have approximately 1.4 as the refraction index. Or do you have to divide it on the opposite direction and you have 0.6? I'm not sure. Anyway, I just want to write 1.0 because 1.4 it seems a little bit too strong and it's not as spectacular. So if I run this program right now, we have a refraction. Incredible. Let's just decrease it even more because we have that annoying effect right in the top, which is actually correct, but they are not look too good. Alright, and then we can use it as a glass or something. So it's a monkey head made of glass. I leave that to you to combine these two effects. You have to use the fractional equation to do that. This is an exercise for you if you really want, or try out and experiment with this program. So feel free to do so. And yeah, that pretty much should conclude this tutorial. So thank you for watching, and